Good morning, students. In today's class, we will discuss properties of Fourier transforms. Assume u and v are two functions belonging to the function space L2 Rn. Rn is n-dimensional real Euclidean space. Then, the first property is to prove that integral of the product of the function u with complex conjugate of the function v over the n-dimensional real Euclidean space. This is equal to integral of Fourier transform of u into the complex conjugate of Fourier transform of v over the space Rn. Second property is the Fourier transform of d alpha u is equal to iota y whole raised to the power alpha into Fourier transform of u. Here d alpha u that belongs to the function space L2 Rn and alpha is the multi-index. Third property is if u and v belongs to the intersection of the function spaces L1 Rn and L2 Rn, then the convolution of u with v, its Fourier transform is equal to 2 pi raised to the power n by 2 into Fourier transform of u into Fourier transform of v. And the last property is the inverse Fourier transform applied to the Fourier transform of function u, that is same as the function u. So these are the four properties. One of the property number 3, we have already discussed before Plancher's theorem. So we will discuss the remaining 3 properties here. Now to prove the first property. In the first property, we are having u and v, two functions belonging to the function space L2 Rn. Alpha is a complex valued number. Let us consider the norm of u plus alpha v. Now, yesterday we discussed Plancher's theorem, and according to that theorem, for a function u belonging to the function space L2 Rn, the norm of the function u and norm of its Fourier transform both are same. So here, applying the theorem for the function u plus alpha v, we can say that norm of the function u plus alpha v and the norm of its Fourier transform, that will be same on the function space L2 Rn. So squaring both sides, we get the square of norm of the function u plus alpha v is same as the square of norm of Fourier transform of the function u plus alpha v on the function space L2 Rn. Now by definition of norm on this function space, this can be written as integral of square of mod of the function u plus alpha v over Rn, and this by using the definition of norm can be written as integral of square of mod of the Fourier transform of the function u plus alpha v over the function space over the space Rn. Now, by using the property z mod square is equal to z into z conjugate, so this can be written as u plus alpha v into its conjugate. In the same way, this can be written as u plus alpha v transform into its conjugate. Now, this can further be written as conjugate of u plus conjugate of alpha into conjugate of v. In the same way, this term can be written as the conjugate of Fourier transform of u plus conjugate of alpha into conjugate of v Fourier transform. This conjugate is the complex conjugate. Now multiplying these two terms, and here also on the right side multiplying these two terms and simplifying, we can see u into the complex conjugate of u, that will become u mod square. We can combine these two terms together under the one integral sign, and alpha into alpha bar, that is alpha mod square, v into v bar, that is v mod square. Also on the right hand side, the Fourier transform of u into its complex conjugate, that will become the square of mod of the Fourier transform. These two terms we have combined under the one integral sign, alpha into alpha bar, that is alpha mod square, and this product will become the square of mod of Fourier transform of V. Now, by definition, this is the square of norm of function u on the function space L to Rn. And these terms we have taken as it is. And this term is alpha mod square into the square of norm of V on the function space L to Rn. Similarly, on the right side, we have these three terms. Now, again, we can use Plancher's theorem. Norm of u and norm of Fourier transform of u, both are same. So these two terms will be cancelled out. In the same way, for the function v also, the norm of v and its Fourier transform, that will be same. So these two terms will also be cancelled out. So we are left with the equation integral over Rn alpha into v into u conjugate plus alpha conjugate into u into v bar is equal to integral over Rn of alpha into the Fourier transform of v into the complex conjugate of Fourier transform of u plus alpha conjugate into Fourier transform of u into the complex conjugate of Fourier transform of v. Now, let us put alpha is equal to 1 in this equation, and then we put alpha is equal to iota. So we get two equations, and after subtracting these two equations, we get integral over Rn u into v bar is equal to integral over Rn of the function Fourier transform of u into complex conjugate of Fourier transform of v. So this completes the first property. Now in the second property, we are to find the Fourier transform of d alpha u. Now by definition of Fourier transform, this can be written as 1 upon 2 pi raised to the power n by 2 integral over Rn of product of e raised to the power minus iota x dot y into d alpha u. Now, using integration by parts formula, this can further be written as minus 1 raised to the power alpha mod upon 2 pi raised to the power n by 2 into integral over Rn d alpha e raised to the power minus iota x dot y into u. This partial derivative of this expression is with respect to x. So we have denoted x in the base to show that this partial derivative is with respect to x. Now, this can further be written as 1 upon 2 pi raised to the power n by 2 integral over Rn. Simplifying this term, this will become e raised to the power minus iota x dot y into iota y whole raised to the power alpha. This term is u. And taking this term outside of the integral, inside 1 upon 2 pi raised to the power n by 2 integral over Rn e raised to the power minus iota x dot y into u. That becomes the Fourier transform of the function u. So we have proved Fourier transform of d alpha u is equal to iota y raised to the power alpha into Fourier transform of u. Third property we had already proved, and the last property is to prove that inverse Fourier transform applied to the Fourier transform of function u, that is u. So let us take u and v belonging to the function space L to Rn. Now let us consider the integral over Rn of the product of inverse Fourier transform of u with v. Now, by definition of inverse Fourier transform for the function u, this can be written as integral over Rn 1 upon 2 pi raised to the power n by 2 integral over Rn e raised to the power iota x dot y into u at y dy, and this term vx dx. Now this term can be taken out of the integral sign. So this becomes 1 upon 2 pi raised to the power n by 2 into double integral over Rn e raised to the power iota x dot y into u at y into v at x dx dy. Now let us consider the integral of product of function u and inverse Fourier transform of v. Again, applying the definition of inverse Fourier transform for the function v. So this integral will become integral over Rn u at y into by the formula for inverse Fourier transform for v. This is 1 upon 2 pi raised to the power n by 2 integral over Rn e raised to the power iota x dot y vx dx, and this dy. Now taking 1 upon 2 pi raised to the power n by 2 out of the integral. So this can be written as 1 upon 2 pi raised to the power n by 2 into double integral over Rn e raised to the power iota x dot y into uy vx dx dy. Now from here we can see that right hand side of the two equations are equal, so left sides will also be same. So we have proved that integral over Rn of the product of v with inverse transform of u, that is same as integral over Rn of the product of inverse transform of v with u. Now let us consider the Fourier transform of complex conjugate of function v. By definition, this is given by 1 upon 2 pi raised to the power n by 2 integral over Rn e raised to the power minus iota x dot y into the conjugate of v at x. So applying complex conjugate on both sides, right side becomes 1 upon 2 pi raised to the power n by 2 integral over Rn. The complex conjugate of this term will become e raised to the power iota x dot y, and the complex conjugate of v bar, that will become v double conjugate, that will be again same as v. And by definition, this is the inverse Fourier transform of function v. So we have proved that the conjugate of Fourier transform of v conjugate is same as inverse Fourier transform of function v. Now let us replace the function u by its Fourier transform in the equation 3. So our equation 3 becomes integral over Rn v into the inverse transform of Fourier transform of u is equal to integral over Rn inverse Fourier transform of v into the Fourier transform of u. Now we can substitute the value from this equation. If you substitute the value of inverse Fourier transform of v, which is this term, so we have substituted the value here, and using the first property here for this integral. So by using the first property, this integral can be written as integral over Rn double conjugate of the function v into u. Now conjugate of function v, that is again v. So this will become integral over Rn of product of the functions u and v. And because this is true for all v belonging to the function space L2 Rn, so we can say that the inverse Fourier transform applied to the Fourier transform of function u, that is same as u. So this proves the properties of Fourier transforms.